Hello students, welcome to the lecture on shortest job first scheduling algorithm. SJF is algorithm in which the process with small CPU burst time would get the precedence over other processes with higher CPU burst time. So the important factor which is part of the SJF algorithm is the size of the CPU burst time for each and every processes. So the small process would get more priority, and it would be dispatched to the CPU before the other processes which were having higher CPU burst time. Now this SJF algorithm can be either preemptive or non-preemptive. In the case of a non-preemptive SJF algorithm, the process would be allowed to complete its full burst time, and after that the next process would be dispatched to the CPU. Now let me introduce this problem to you, which we are going to solve using SJF algorithm. There are three processes, P1, P2 and P3, and arrival time is given respectively here, and this column represents the burst time for each processes. So based on that, the process 1 arrival time is 0, P2 arrival time is 1, P3 arrival time is 2. The smallest process here is P3, the biggest process is P1. However, at time 0, only one process available in the ready queue, hence the process 1 would get the CPU first. Even though the process 1 is big, but at time 0 in the ready queue there is only one process, P1. So we cannot compare the P1 with any other processes at time 0, and the P1 is dispatched to the CPU, and the P1 starts its execution with the CPU, and at time 1 the process 2 comes to the ready queue, but this algorithm is non-preemptive. Since it is non-preemptive, the process 1 is not preempted. It is not taken out from the CPU. It is allowed to continue until it completes its full CPU burst time. Now let me draw the Gantt chart. So the process 1 starts the execution at time 0, and it continues until 8 milliseconds. And let's say this is context switching. This is context switching. Okay, so next once the process 1 completes its task, okay, there are two other processes remaining in the ready queue. One is P2 and P3, and both have arrived already in the ready queue. Process 2 has arrived at time 1, and P3 has arrived at time 2. Now we have to compare their burst time in order to find which is the smallest process. So based on the burst time, it is clear that the P3 is the smallest one. So next P3 would get the chance instead of P2, and it would start its execution from 8, and it will continue until 10. Okay, So just assume that it is sorry it is P3 is starting its execution at 8 and it is completing its task at 10. And again, uh, here there will be a context switching. And now P3 will get the chance. So P3 will start at 10 and would complete at 14. So this is the Gantt chart for this given problem. This Gantt chart we have derived using the SJF non-preemptive type. And let's calculate the waiting time. The waiting time for the process 1 is 0 because it starts the execution at 0 millisecond and its arrival time is 0, so its waiting time is 0. Regarding the process 2, sorry, I made a mistake here. This is process 2. Regarding the process 2, it gets the CPU at 10 millisecond and its arrival time is 1. 10 minus 1 is 9. And third, the process 3 waiting time is 8. It starts the execution at 8, so 8 minus arrival time is 2. 8 minus 2 is 6. Okay, now turn around time process 1 turnaround time is, it is completing its task at 8 milliseconds, so its arrival time is 0. 8 minus 0 is 8. And process 2, it is completing its task at 14 milliseconds. Its arrival time is 1, so 14 minus 1 is 13. And regarding the process 3, its arrival time is its completion time is 10. 10 minus arrival time 2 is 8. So let me check. 8 minus 0, P2 14 minus 1 13, and P3 10 minus 2 is 8. Okay, so this is how we calculate the waiting time and turnaround time. Now let us solve the same problem using preemptive algorithm, SJF preempting algorithm. So P1 starts its execution since at time 0 only P1 was available in the ready queue, so it is starting the execution at time 0, and this execution will continue until 1 millisecond. Because at 1 millisecond new process is coming to the ready queue, that is P2. Okay, so P2, there is a context switching taking place, and P2 gets the chance and it starts its execution at 1 millisecond and it continues until 2. When at time 2, please see that, for example, when the P1 starts at time 0 and time 1, it has already completed 1 CPU burst millisecond. So remaining burst time for the P1 is 7 at this moment. Okay, how much? 8, 7 is remaining. So now at time 1, a new process P2 is coming to the system. Its burst time is 4. So you compare when the system compares the burst time of the P1 and P2, it is clear that the P2 has smaller burst time, so it is a smaller process than P1. So immediately the context switching takes place. Since it's a preemptive scheduling SJF algorithm, the process P1 is preempted and the CPU is given to the process 2. So the process 1 is sent to the ready queue now. It's waiting in the ready queue now with a burst time of 7. Now the process 2 gets a chance. So process 2 starts the execution at 1 millisecond. It continues until 2 milliseconds. So at 2 millisecond, what happens? Its burst time is reduced from 4 to 3. But you can see the table at time 2, a new process P3 is coming to the system, and the P3 burst time is only 2 milliseconds. So when the algorithm compares the P3 and the P2, it finds that the P3 is smaller than the P2. So again here context switching. So context switching takes place and the process 3 gets its turn. P2 is preempted and the CPU given to process 3. So process 3 starts its execution at 2 milliseconds and now it can continue until its burst time expires. So 2 plus 2 is 4. Now the P3 is finished. Now P3, now what happened? All its burst time finished. So it becomes 0. The process 3 is terminated. Now in the ready queue there are two processes available. One is P1 and P2. P1 burst time is now 7, current size is 7, P2 size is 3. So the algorithm finds that the P2 is smaller than the P1. Okay, so again the P2 gets the chance. It starts the execution at 4 milliseconds and it can continue until 4 plus 3 is 7 milliseconds. Okay, so here actually context switching should come. So process 2 gets the chance. And it continues its execution until 7 millisecond. Now the process 2 also expired. Process 2 also expired. So only one process remaining in the ready queue, that is P1. So P1 will get the chance now finally, and there are 7 milliseconds remaining with the P1. So it will run. It starts at 7 and it will continue running until 14 milliseconds. So this is how we draw the Gantt chart for the SJF preemptive algorithm. Now we calculate the waiting time for the P1, waiting time for different processes. P1 we'll do first. So P1 was waiting here. Okay, so from 7 minus 2 5, it was waiting for it was waiting from 7 minus 1 is 6, and arrival time is 0, so it was waiting for 6 milliseconds. How I calculated? 7 minus here 1. So here it is waiting, process 1 is waiting for 1 millisecond, and here it is waiting for 2 millisecond. So 2 plus 1 3, and here 3 millisecond it is waiting. So totally 6 millisecond it is waiting, and its arrival time is 0, so its waiting time is 0. Then process 2 was waiting here 1 millisecond, and then it was waiting here for 2 millisecond. So 2 plus 1 is 3, and its arrival time is 1. 3 minus 1 is 2. And process 3, it was waiting from here to here, so it was waiting for 2 millisecond, and its arrival time is 2, so 2 minus 2 is 0. Now turn around time for the process 1. P1 completes its task at 14 millisecond, and its arrival time is 0, so it is 14. And process 2, it is completing its task at 7 millisecond. Okay, and its arrival time is 1. 7 minus 1 is 6. And process 3 is completing its task at 4 millisecond. 4 minus its arrival time is 2, so 4 minus 2 is 2. So this is how we compute the Gantt chart waiting time and turnaround time for the SJF preemptive algorithm. From this you can understand clearly the logic behind the SJF algorithm preemptive and SJF algorithm non-preemptive. Thank you very much.